In this video, I introduce a deep face verification using facial vector. Facial vector is used for unconstrained face verification, which is computed from detected orthofrontal faces. Facial vector encoding and the joint Bayesian metric are trained in the labeled face set to find the weight, mean, vector, and the covariance matrix of a Gaussian mixture model. The query phase goes through face detection, landmark localization, feature extraction, and facial vector encoding, and then is classified by using Bayesian metric. The pipelines of the model training and testing are shown here. 3 steps are used to obtain a frontalized map of a face image by a 2D to 3D correspondence of a reference image from a 3D face database. Suppose that C is a camera matrix that transforms 3D coordinates P to 2D coordinates P of facial landmarks here. Given an input image in a non-frontal pose, L is the detected landmarks which are used to generate the 3D surface coordinates P. The rotation matrix R and the translation vector T are used to generate the pose in the given input. Using the estimated rotation and translation parameters, each pixel in the input image is warped onto a location in the frontal view, and the color at each pixel is computed using bicubic interpolation. GMM is used to represent U lambda, where the parameter lambda is the tuple weight mean covariance of GMM. Suppose that the covariance matrix of GMM is diagonal. The first order and the second order derivative of phi1 and phi2 of facial vector phi with respect to mean and variance are computed by using these 2 formulations, where coefficient alpha is computed using this formulation. The final facial vector for image I is a concatenation of phi1 and phi2, where V, P, and N are the feature vector and its number, respectively. Once a facial vector is encoded for 2 face images, the joint Bayesian metric learning models a joint distribution P of 2 images xi and xj as Gaussian. Sigma and sigma e represent face variation of the same identity and different identities respectively. If xi and xj belong to the same identity, the joint probability P belongs to normalization with covariance sigma I. If xi and xj belong to the different entities, the joint probability P belongs to normalization with covariance sigma E, as shown here. In this way, the similarity measure between 2 images are converted into a binary classification problem, namely the joint conditional distribution P of 2 images, xi and xj belongs to the distribution with covariance sigma I, or the joint conditional distribution P of 2 images, xi and xj belongs to the distributions with covariance sigma E. For more details, please check with these references. Thank you. Bye.